please wait for the mic.
Well, Mark asked, excuse me, Mark asked me to talk about physics issues needing further study, and when I first started writing this talk, I thought, well, gee, what I'm going to do is go through and see which processes we had good simulations for and which ones we needed better simulations and so forth. But I started doing that, and I realized that wasn't what I wanted to say. What I wanted to talk about here was why on earth are we building this machine? So that's what I'm going to talk about, is my take on why we're building this and how we should go about convincing other people that we really have our act together and we really understand why we're building this, what the physics is. So to me, that's the challenge ahead, is to convince our colleagues that we know what we're doing. So I'm going to talk a little bit about electroweak symmetry breaking. Can we understand it? Do we know what we're doing? A little bit about SUSY, but not too much. We heard quite a bit about the top quark, and I'm going to point out some holes in our understanding of top quark physics at a linear collider, and then new ideas and hard work. Okay. So after I got here, I realized that this talk is really my answer, my start of an answer to Paul Granis's question and challenge on the first day. Why should a 500 GeV linear collider be started before the LHC is given physics results? Why do we think we know what we're doing so that we can build it now instead of waiting 6 years from now when we have presumably a Higgs and SUSY particles and whatever? And I have a lot of points in my talk about what we need to do to really firm up this argument. I think we need to push and prod in the corners of this argument so we can really convince ourselves that those holes that are there in the argument, that we understand them. Okay. So as Paul said, the major physics goal for building a linear collider is to understand electroweak symmetry breaking. And we have a really beautiful picture of the logic of how this goes. So is it the Higgs? Well, we have precision measurements that tell us that the Higgs, if it's a standard model, is less than about 200 GeV. The LEP electroweak working group had 222, which was in Michael Peskin's talk. This particular number is from the SNOMATS precision physics group. The exact number depends on which pieces of information you put in, but it's not really relevant for this argument. So we think we know that the Higgs is light. We think we can observe the Higgs easily through the Higgs string, E plus E minus to ZH. And furthermore, we know exactly where to go to do this. This is just a simple plot of the cross-section. The red doesn't show up very well here, I guess. A simple plot of the cross-section for producing E plus E minus to ZH is a function of the energy. And this black curve here is Higgs drilling. And in this particular plot, the Higgs mass is 115. And you see the cross-section rises, and it has a maximum just above the threshold for producing the Higgs. So we know where to build this machine, too. Just above the ZH threshold is the optimal energy scale. So if the Higgs is less than 200, if you have a machine of 500 GeV, you're kind of over here. If you have a machine of 350, you're up here. And there's about a factor of 2 difference in the cross-section for this process between 350 and 500. So you have to be very careful when interpreting the Tesla numbers, because a lot of the differences, as Michael pointed out in his talk, are just due to the difference in statistics from this factor of 2 of the energy. So we know where to look for the Higgs. We know how to look for it. And so now the precision measurement of the Higgs mass is straightforward. And an important point here is that this precision measurement of the Higgs mass is absolutely independent of the Higgs decay. No matter what theory we've constructed, this is just a missing mass experiment. We just construct the missing mass from the Z decays, and we can measure this cross-section to roughly 2%. Okay, and these are plots from the Orange book showing at 350 and 500 GeV the Z decay to mu pairs, and you can see these sharp spikes here for the different Higgs masses over the background. Is the stuff at the bottom, and you notice it's a little bit narrower at 350 rather than 500. Okay, that's just due to statistics, and we can measure the Higgs mass to 80 or 140 GeV in this intermediate mass range here. Let's see, those numbers there are for 120, I believe. And the point is that was made in Sven Heinemeyer's talk on Monday is that the Higgs mass is a precision observable in SUSY models. Because in SUSY models, we predict what the Higgs mass is as a function of all the other parameters. So the better we do on this mass measurement, the better we can understand the supersymmetry structure. Okay. Okay. And then, of course, we can match this direct measurement of the Higgs at the linear collider with the indirect measurements. At a linear collider with 500 inverse femtobarns, we'll measure the W mass to about 10 MeV, which will give an indirect measurement of the Higgs mass of about 50 MeV. And this is from the SNOMAS proceedings here. Okay, so you can ask, well, what are we going to learn? Why should we care about a 50 MeV measurement of the Higgs mass? Well, there are two reasons. First of all, there's the point that it's a SUSY precision observable that I've already made. And the other point is that the direct measurement and the indirect measurement had better agree. You better get the same answer if it's a standard model. And this is just a plot from SNOMAS illustrating this point. This is the W mass as measured directly. And here are the experimental bounds right here. And this is the Higgs mass extracted from our current error on the top quark mass. Okay, so here we are. And you see that these things are pretty close up here. So as we build the linear collider, this band is going to shrink and shrink and shrink. And so these two things have got to agree. Okay, well, this is a nice picture. It really looks like we know what we're doing. So so the question is, can we get around this picture? Can we evade this Higgs mass bound? Is somehow there's some hole in our logic that tells us, well, gee, maybe we aren't so sure of ourselves as we thought we were? Well, the Higgs self-coupling scales with energy. So in the standard model, the Higgs has a cubic interaction which scales with a, this is a terrible printout, which scales with a coupling lambda, and a quartic coupling which also scales with the same coupling lambda. And the point is that this parameter lambda, the Higgs quartic coupling, goes to infinity at some high scale. So we know exactly how it scales with energy. Q squared is the energy. And it scales with lambda squared. So the heavier the Higgs, because lambda is related to the Higgs mass, the smaller the scale lambda at which this coupling goes to infinity, and our theory no longer makes sense. So what's this mean operationally in terms of a linear collider? Well, first of all, once the Higgs quartic coupling has blown up to infinity, we no longer have the standard model. We've got to consider the standard model some effective theory that's just valid below this scale lambda. So here's the scale lambda, and here's the scale at which the Higgs self-coupling blows up to infinity. And you can see, if you're going to have a Higgs which is heavier than this bound of 200 GeV or so, well, then you're going to have the scale lambda be relatively low. So for example, if there's no new physics, no new physics before the Planck scale, well, then we have this bound that the Higgs mass is less than about 200 GeV. Oh, that's much better. But as you get down to have a Higgs mass of, say, 400 GeV, you want a heavier Higgs, say one that you wouldn't make at the linear collider. Well, the scale of new physics is 10 to the 4th GeV or something, so it's relatively low. And no matter what kind of model you construct, you really can't get around this argument that if you're going to evade the Higgs bound of 200 GeV, then you're going to have new physics on a relatively low scale.
Mike Ronan?
Where's your duct tape? That's what all experimentalists need. That's how you build a linear collider, is duct tape. Okay, so how can we get around having a light Higgs? Well, we need a non-zero S or delta T in order to have a heavy Higgs. So either we've got to give something that gives delta S a kick negative, or it gives delta T a kick positive. Okay, so you can go and look for models that actually do this. Okay, and this paper of Mike Volpeskin and Jim Wells just went through all the models that they could think of to look and see what happened when you evaded the light Higgs bound by putting in some new physics. And they kind of fell in three classes. There was either a new Z prime at the weak scale, because in order for this Z prime to do something to fix up the electroweak precision measurements, it had to be relatively light. You could do it with large Higgs multiplets, which I removed my comment was a disgusting model, but it's certainly possible. And there tend to be light technipions, which you would also see. Or else you would have, in order to mock up the delta S and delta T to evade the precision data, you have shifts in precision electroweak data, which you would be able to see at the linear collider. Well, this is kind of an important argument, the statement, well, gee, if we don't see a light Higgs, then there has to be some other stuff. So, well, maybe we just haven't made the right model. You can ask, okay, well, these folks looked at all the models they could think of, but maybe we just haven't thought of the right one. There's no argument that we haven't. So let's just look at the standard model as an effective theory. So we've got the standard model. We'll just write down all the operators that we can write down as in powers of 1 over lambda squared. So these are operators, which are actually dimension 6. We'll write down all the operators which are allowed by the symmetries and see if we can learn anything about the new physics. Well, the first operator you might write down violates the symmetry that has rho equals 1, and it fixes up the electroweak interactions. And it's an operator that has a Higgs and a derivative coupling of the Higgs. So what does this mean? Well, you put in these effective operators, and you can get heavy Higgs. This is a particular plot was made by Sekar-Shavukla right here, and this is a plot of the limit on the Higgs mass as a function of the contribution to delta T from this new operator. So this flat line here, it's a standard model where there's no new physics. And this point right here is 222, so this is the left electroweak limit on the Higgs mass from precision measurements. And as soon as you turn on these new operators, you can go off this flat line, go up here in this region, and you can get Higgs masses 450, 500 GeV with large new operators. So the challenge is really, can you build a model that does this? And I think theorists have a lot of work to do building models that actually generate these delta T's, because obviously now you can have a heavy Higgs and you get this non-zero delta T, but this isn't a real model. This is an effective theory. And you can go even further and just remove the Higgs altogether from your theory and just fit the electroweak data. So this is a challenge to the theorists. You know, go home, all these models that Joe Licken talked about, he had 1 million models. Can we evade these Higgs bounds in these models? And if so, once you've done that, do they have consequences that we can measure? So I think this is a bit of logic we need to continue to the end. Okay. All right, so returning to the standard model here, what do we have to do with the standard model? Well, the statement is, we know the Higgs is there, we can find it, so we want to measure the Higgs couplings, because the measurement of these couplings is supposed to test the standard model, because the couplings of the Higgs to, say, fermions is absolutely predicted. It's proportional to the mass. So we have 2 questions. How well can we do? That's an experimental question. And how well do we need to do? Okay, so this plot is a plot by Marco Battaglia. Okay, so this shows the standard model Higgs branching ratios as a function of the Higgs mass. It only goes out to 200 GeV. So on this plot, most of the decays are to BB bar. And this particular plot was made for Tesla, so it's an energy scale of 350 GeV with 100 inverse femtobarns. And of course, I've said this before, get larger errors at 500 GeV. So these black dots are the errors you would measure experimentally with the 100 inverse femtobarns, and the blue bands are the theoretical uncertainties. And you should note on this plot that the theory uncertainty is larger than the experimental uncertainty, telling us again that theorists have more work to do. And the biggest uncertainty that goes into, say, this blue band for BB bar is from the mass of the B quark. In this particular plot, he took the epsilon, the 1s mass, and it's 4.2 plus or minus 0.11. If you look in the particle data book at the B quark mass and try to figure out exactly which B quark mass to put in here, any individual measurement for the B quark mass or extraction has smaller errors. But when you put them together, there's actually a fairly large spread here. Okay, so this is the largest error on the predictions. Okay, so how well do we need to do? Well, these Higgs couplings are supposed to distinguish between, for example, the MSSM and the standard model. And the MSSM is a hard case because as the mass of the pseudoscalar goes to infinity, all the couplings go to the standard model. And infinity is actually a fairly small number. It's typically 300 GeV or so here. So this is a hard call. So here's just one example, okay, to compare what we can do with what we can learn. So this is 500 GeV, 500 inverse femtobarns, and these are errors on coupling constant measurements from the Oregon group at Hopkins last summer. Okay, so roughly 20% on the gluon coupling and 9% on the W coupling. And then you can compare them with Susie, what you might get. Okay, so this is Heather Logan and her collaborators. Heather showed these plots here, I believe. For a particular choice of Susie parameters, so for the gluon coupling, this brown line is 15%, relatively the same here. And you could see that it doesn't distinguish very well in tangent beta, but it does measure a little bit MA. And similarly, here's for the W. So 9%, here's the 0.1 line. It's not very sensitive at all. And of course, these plots exist for all the different couplings. I just picked these out randomly. So you can ask, can you distinguish between models by measuring this? And of course you can. Okay. If you measure any two couplings, they're going to be different in different models. So the new physics is going to change the Higgs branching ratios in different ways. For example, Joanne Hewitt talked about this particular model yesterday. This is the Randall-Sundrum model, where you have an object which is called a radiant, which looks a lot like the Higgs boson. And it mixes with the Higgs boson, and it changes the Higgs couplings. So this is the change in the coupling to the gluon from this new object. Okay, so there are different sets of parameters here. And you can get fairly large shifts. You know, here's the ratio -1, 2, -1. And this plot, if you compare it with my previous plot for gluon couplings, is quite different. So by measuring these different things, we might have an understanding of what happens. Okay. The other mantra that we always have, that what we want to do with a linear collider, is we want to see if it's electroweak symmetry breaking. So to verify electroweak symmetry breaking, we have to test the structure of the potential. Well, this sounds pretty good, but can we really do this? Well, we know that the Higgs couplings have this parameter lambda. This is just another way of writing the interaction I had before. So we need to measure the trilinear couplings of the Higgs. Well, this is going to be a hard business before you even start. Because if you just calculate the cross-section for a process which involves the trilinear coupling of the Higgs, say ZHH, it's pretty small. It's 0.2 femtobarns, even smaller. This is 120 GeV Higgs. Okay. And there are huge electroweak backgrounds to processes like these. Okay, and I wrote here that you need real simulations. We heard about a simulation that was going on yesterday, and this simulation that was going on was interesting because with 2,000 inverse femtobarns, so I might still be working after 2,000 inverse femtobarns, I don't know, but you only have 18 signal events and 33 background events. So measuring these trilinear couplings is a hard business, and we have a lot more work to go. Okay. Okay. Let's see here. Okay. Well, as we continue on our process of verifying that we really understand electroweak symmetry breaking, we also have one more thing to do. We not only have to measure the couplings and measure the self-couplings, we also have to show that this is really a scalar. Okay, and usually we say that the way we're going to do this is by measuring the threshold behavior, E plus E minus goes to ZH. Let me just point out, this is another argument for having a machine that can run at the ZH threshold. Not only are the branching fractions more easily measured, but the spin dependence you can measure. Okay, so as you scan through the cross-section as a function of the energy, the shape is quite different depending on whether you have a spin 0, spin 1, spin 2 object. And there are a lot of other handles on spin, and I think we need some real simulations on these. We heard about one yesterday. We're looking for the Higgs decaying to tau pairs and the taus decaying to pi's and rhos, and you're going to measure the angle between the pions and the rhos to see what the spin of the Higgs is. And I forget what the comment was, that this was, are you here? PDD13, pretty darn disappointing. I'm not sure I got that right. But it looks very hard. So this is another area where we really need more work to see if we can really do this. Can we prove that this is a scalar? Okay. All right. So I'm going to skip supersymmetry, not as a value judgment, but just to continue and briefly talk about the top quark before concluding. Okay, the top quark. One of the other reasons that physics goals underlying the linear collider is to really understand flavor symmetry breaking and why quarks have different masses. And the top quark is really a laboratory for understanding flavor symmetry breaking. So we can build models where a top quark gets masses from extended technicolor, top color, whatever. And these models turn out to be extremely difficult to construct. And as we go through these models, they all kind of lead to theories with strong top interactions. And this is a motivation for precision measurements of top properties. So we hope that at the linear collider we can really measure these top quark properties. And let me just show you an example here. Okay, the TT bar threshold. Lawrence Gibbons showed these plots also. It's an example where theory has made tremendous progress in understanding what's happening. This left-hand side here is the status a few years ago. This is the energy of the machine, and this is the cross-section here. And this is just a pole definition of the top quark mass. And we've got lowest order is what, dot dashed, these three curves. The three curves are three different renormalization scales. And then next to leading order, next to next to leading order. And the position of the pole mass was moving all around. So once we understood what definition to use for the top quark mass, we get the right-hand side, where as you go from lowest order, next leading order, and next to leading order, the position of the pole mass stays in the same place. And we have roughly a 20% uncertainty here due to the scale uncertainty. Okay. So with 50 inverse femtobarns at a linear collider, we're going to measure the top quark mass to 200 MeV. And you can compare this with the LHC, which is going to get 1 to 2 GeV. And this 200 MeV will feed into, of course, our extraction of the Higgs mass from precision measurements. Okay. So theorists have gone even further and summed the next to leading logarithms. So they've summed the logarithms, which are mt over lambda QCD, and the theory is now good to roughly plus or minus 3%. So you can use the threshold measurements to measure the width, alpha S, GTT, H, and this is just the plot for alpha S variation. Okay, and several comments here is for this level of precision, as I've said before, the theory has to match the experiment, and you have to have the electroweak effects, which don't exist yet. Okay. Realistic simulations have started on these processes. For example, we heard that with 300 inverse femtobarns, you'd measure the top Higgs-Yukawa coupling to roughly 20%. And again, this measurement is also limited by theory, because in order to get the measurement of the top Higgs coupling to 20%, you had to use asymmetries and the momentum distribution, which don't exist to next to leading order. Okay, so okay. And the top quark is also a laboratory for QCD corrections for production and decay. And the top quark is not only interesting to see if we can understand flavor physics, but also as a background for any new physics that we think we might have. Top turns out to be a background. Okay, I guess I've mentioned this about 6 times before. So if you do the full calculation, E plus E minus goes to TT bar, goes to leptons, jets, and Bs. For the total cross-section, it doesn't make much difference whether you just use the double pole approximation or the top on shell here. But when you try to make momentum distributions, it actually makes a difference if you let the top quark be off shell here. And there's still a lot of work needed to be done to do these full calculations with different distributions. Okay, well, this is all very nice, but can we really do all this? Okay. A lot of these measurements take 500 inverse femtobarns, 1,000 inverse femtobarns, 2,000 inverse femtobarns, lots of luminosity. So one thing that happened at SNOMAS, which I thought was really important, was the E3 working group here tried to see if you could construct a running scenario where you could really do all this stuff, because you can't, it's not very satisfying to say, well, if I have 1,000 inverse femtobarns here, I'll measure this. because what we want to do is scan through all the SUSY masses. So they picked a particular SUSY scenario where they got all the SUSY masses, and then they made luminosity assumptions, which added up to 1,000 inverse femtobarns. So in 7 years, they said, well, maybe it turns on kind of like this. And then they saw what they could do with this 1,000 inverse femtobarns. So they had a plan where you did threshold measurements of the top quark, you scanned through the SUSY parameters, and what they found was they could make a reasonable plan where you would measure the SUSY thresholds and get the masses to 0.2 to 0.5 GeV, get the Higgs mass and couplings to roughly 1.5%, and do a top threshold and get the top mass to roughly 150 GeV. And I think we need to construct a few more of these scenarios. What's that? MEV. Where's my pen? MEV. Thank you, Tom. That's why I have to be cool and do these with my computer so I can change them. We need to construct some more scenarios and see if we can do this in random scenarios as opposed to just one. Sven Heinemeyer showed a whole lot of SUSY benchmark scenarios, and we should see if it's really possible to go through these.
Sally, was there also an agreement on what energy you run out at each one of those years? I mean, you can imagine.
Yes, John is here, and I think Jim is too. They have a table where they go through the different energies. So they scan through the different SUSY masses to get the precision, and after they'd scan through the SUSY masses, then they'd move on to the next one. Yeah. So an absolutely essential ingredient in this plan was being able to easily tune the energy up and down.
But you can imagine competing physics goals. So
right, absolutely.
To sit at 350 for a long time, somebody else wants to.
Right, and I mean, that's why this exercise is so important, is to go through and see.
Can you clarify this? Because I thought that the main conclusion in that working group was that most of the running is at the top energy, and one does a little bit of adjustment.
John, you're here.
Paul is really the one who should answer.
In the SPS1 scenario, which is what we've done
Wait a second, Paul.
It was the SPS1 scenario that Sven talked about, and about roughly half of it is at the top energy.
Right.
A lot of it is at fairly high energy, and then the rest of it is down 300 GeV-ish for the particular thresholds that one wanted to scan here.
Right. So it moved around, yeah. I'm sorry I didn't bring the slide which showed exactly how they split it up, because that particular split up is going to depend on the model. Okay. So let me just conclude here. There's a lot of hard work ahead. There's wonderful work from Snowmass 2001. Every time I log on in the mornings, there's another proceeding there with nifty results, and I look forward to seeing the working group reports soon. We have a game plan now. We have a game plan for determining the origin of electroweak symmetry breaking. We're going to measure the Higgs mass, the couplings to fermions, gauge bosons. That's going to tell us, is it the Standard Model, is it SUSY, is it something else? This is great. We're going to measure the Higgs self-couplings, determine the structure of the potential. Well, we need a lot more work here to see if we can really do this one. Sounds good, but we need some more work. Measure the spin of the Higgs. Okay, so there's serious simulations needed for a lot of these processes to see if we can really do this. We need more model building out of the box, like Joe talked about. We need to build these models and have the strength of purpose to continue and firm them up so that we can see if the models that don't have the light Higgs have other things we can measure. Okay? And I didn't really talk about a TeV, but I believe we need to firm up the case for a TeV linear collider. A lot of the stuff I talked about, the trilinear couplings of the Higgs, the TTH measurements, are pretty marginal at 500 GeV, and we really need this higher energy. Okay, and finally, I didn't write it down here, but we need to have theorists do these really hard two-loop radiative corrections so that our theoretical precision can match with our experimental precision. Okay, so let me stop here.
Thank you. So we have time for questions and comments.
Michael?
Hi, Sally. You're a little unlucky to be standing up there, but what worries me is that we start off with a lot of gusto saying that we can measure all the properties of the Higgs, and then out of your list of 4, you kind of die on number 2.5. And I'm a little nervous that we.
Oh, you mean this one?
Yep.
Well, gee, I could have written that differently. Yeah. So, but you know that we're going to measure the couplings to the Higgs, to the top, to the B, to the W, the Higgs mass. I mean this.
No, I'm sorry. My point is that you have 3 bullets.
These 3.
Right. And we
I
are
think-
halfway down that list.
I think he means that the self-couplings are marginal.
Yeah, that's absolutely true. We should
But
do
spin
some more
is
work.
easy.
The spin actually.
Spin is easy.
Yeah. Well.
I mean, as easy as anything is, right?
See. Right.
Sally, I'm going to another point. The fact that the precision electroweak bounds the Higgs mass, except in a limited class of scenarios, is very important. And you said that we considered all models we could think of, but I'd like to qualify that just a little. Jim Wells and I really tried to review the literature systematically. The original
Right,
ST
I didn't mean to be
paper-
flippant. You did
The
go
original
through it.
ST paper has more than 700 citations, and we did a quite systematic review.
That's-
Now, whenever you publish a paper where you say there's no theory that does such and such, you get a lot of email. And in fact, if you look on HepPH, you'll see that we're up to version 3 in the postings of our article, with an increased number of references in every posting. But so far, all the email that we've gotten fits into one of those 3 classifications, the 3 different signatures of models that do not have a light Higgs. So, frankly, personally, I believe that we've reached asymptopia. I don't know whether Jim Wells agrees with this. And, of course, if anyone has a counterexample, they can send me more email, and we'll post a version 4. But I think this theory space, in terms of just what's going on with the Higgs, is quite well mapped out. And I really think that whatever happens, the linear collider will have something to say about it.
I don't disagree with that, but I will point out that there's still these models of the general school constructed by Secker, which have the heavy Higgs, but these aren't real models. These aren't real models. This is so right. Maybe we just haven't constructed the model that gives us this picture. And what you're saying is, yeah, there have been a lot of models and nobody's done it yet.
Well, the
Right.
top quark seesaw model of Debrescu and Hill and Cheng does this.
Okay, right.
But but that's
Right,
the
that has
that's the
those
category where you have a shift in the precision electroweak
Right.
observables,
Yeah.
which is a rather indirect
Yeah.
discovery of new physics.
Right, I'm not disagreeing with you. I'm saying that we really need to push in the corners of that because it's a critical argument.
Are there more questions and comments? I guess I'd like to get back to the thing that Mont raised for the case when the Higgs is still what we call light, but above the 2MW, and so that just by its nature there are fewer things that are very accessible. The BB bar decay is a weak decay, and
Right.
How do we address that in making the case? Because people will bring it up.
Right, thank you. I forgot to mention that, actually, that a lot of these studies, when you look at, they always choose the Higgs mass to be 120 GeV. And a lot of stuff gets really hard, even as you go to 130, forget 160, 170. And that's something that, we really need to work on. Because I don't know if you're sensitive to 180 GeV Higgs at a 500 GeV collider. That's one of those comments.
Sally made one point which I think is important, and that's this issue of the case for the 1 TeV, or whatever that number is up there.
Right. Big number, right.
Big number, whatever that number is, because that's one that's going to be important for the machine discussions down the road. It's sort of important for things such as you was asking about, the question of the top couplings as well as the Higgs self-couplings will be important for the upper ends of the machine. But for the machine discussions, that question is going to be one that we need some real discussion about, is what that number is, how important is it up there, how soon might you want to get there, and things of that sort. So that's just a comment back of one you would highlight on your list. I think.
Right. It was in pink.
To be cynical, isn't the answer to that question, wait and see what the LHC shares us?
No, I don't believe the LHC is going to do much in the way of measuring the Higgs self-couplings. That's extremely hard to do.
what is the top energy? What energy do you want ultimately to go to? Depends very much on the scenario.
Right. I mean, depending on the SUSY spectrum, 800 GeV might be enough. You might want 1.5 TeV. Is there?
The question might be, you always want to be able to get another 100 GeV.
Okay. Dave Burke said you always want another 100 GeV. Okay. Well, I don't see any hands waving, so let's thank Sally again and move on to the next speaker.